Hello everyone. The topic today is about aircraft dynamic stability. Note that the dynamic stability analysis is concerning the time history of the aircraft motion when it is perturbed. So let's start by looking at the simplest case of a 1 degree of freedom, pure pitching motion. In this case, the airplane CG is constrained to move in a straight line at constant speed, but the aircraft is free to pitch up and down about its CG. So this pure pitching is just a 1 degree of freedom motion. This constraint is what you normally do in the wind tunnel test. Let's start analyzing the dynamic stability of this motion by developing the equation of motion. For pure pitching motion, the equation is simply the sum of all pitching moments about the CG equals to the moment of inertia about the y-axis times the pitching angular acceleration. If we apply small disturbance theory and assuming no moment at the reference condition, we get this equation of the perturbed motion. The pitching moment term is then expanded. Here it is described that the pitching moment is a function of the change in angle of attack, the rate of the angle of attack, pitch rate, and the change in the elevator deflection. These are essentially the only parameters affecting the change in the aircraft's pitching moment. So we take the partial derivative of the pitching moment with respect to the change in the motion variables. We can simplify the equation further by assuming that the aircraft's flight path is constant. This signifies that the change in angle of attack and the pitch angle are identical. This assumption is valid in this case of a 1 degree of freedom motion where we constrain the aircraft CG such that the aircraft moves in a straight line and it is only allowed to pitch up and down about its CG. So we can equate the angle of attack equals to pitch attitude. Likewise, the theta dot equals to alpha dot, which signifies the pitch angular velocity. We can also equate this Euler angular velocity, the theta dot. We equate that to the body fixed pitch rate, Q. With this assumption and simplification, the equation of motion is now described in terms of one variable, which is the angle of attack and the derivatives of it, and one input variable, which is the elevator deflection. The equation of motion is then rewritten in terms of the stability derivatives. These stability derivatives are essentially the partial derivatives divided by the moment of inertia. So now that we have derived the pitching moment equation of motion, which is the one down here, now let's analyze the dynamic stability of this motion. Notice that the equation is a second order linear equation. We can take the Laplace transform to convert the equation from time domain to S domain. In S domain, we take the homogeneous part of the differential equation. This is also called the characteristic equation. And the roots of this equation will give us the solutions to the differential equation. A general second order system can generally be described by this characteristic equation, which is in terms of the system's damping ratio and natural frequency. So we can compare the characteristic equation of our aircraft's pitching motion to the general second order characteristic equation. From the comparison, we can deduce that the natural frequency is affected by m alpha stability derivative, while the damping ratio is affected by these terms. When the values of the natural frequency and the damping ratio has been computed, we can compute the roots of our pitching motion equation using this equation. We can get the solution to the differential equation by looking up the Laplace transform table or by taking the inverse Laplace transform to get the solution back in time domain. So this is the solution to our equation in response to a step input of elevator deflection. Note that this solution is in time domain. If we plot this solution on a graph of angle of attack versus time, the graph will look like this. So the shape of the response graph will depend on the value of the damping ratio, as well as the natural frequency and the phase angle. We can see from these equations that these values depend on the stability derivatives. The stability derivatives, the value of these derivatives would change as the flight conditions change. So it depends on parameters such as the aircraft's airspeed or altitude. So essentially in dynamic analysis, we want to analyze how our aircraft's response would look like in a specific operating condition. We can also do dynamic stability analysis without looking at the aircraft's equation of motion. We instead look at how the aircraft responds to a certain input. We then analyze the response plot in time domain. Here's an example of a plot of the aircraft's pitching angle or angle of attack with respect to time. In this case, an initial disturbance is introduced in the pitching angle. We then take a look at how the aircraft's returning back to its equilibrium position over time. The response looked like a second order response in an exponential decay pattern. This graph essentially can be expressed by this equation, and the envelope of the decay is expressed by this exponential. Notice that these equations, they are functions of the damping ratio and natural frequency. So this means that we can compute the natural frequency and the damping ratio of the system from this time response graph. This shows that there is a direct relationship between the frequency domain parameters, such as the roots, damping ratio, and natural frequency, and the time domain parameters, such as the period and time to half amplitude. From this equation, we can see that the frequency, which is the damped frequency, can be obtained from the period of the response. Period is obtained. Period is essentially the time it takes to complete one oscillation. From this graph, we just take the time between one peak to another peak of the oscillation. From this equation down here, we can see that the parameter eta, which is the damping ratio times the natural frequency, can be obtained from this graph. It can be obtained from the time to get to half amplitude of the response. So the time to half amplitude is obtained by taking a look at the envelope of this exponential decay, and we take the time it takes from one known amplitude, for example y1, to an amplitude that is half of the initial amplitude. So that time can be directly translated to the damping ratio and natural frequency of the system. Alright, so the motion that we have covered so far is only the case of a 1 degree of freedom motion, and we have covered an example of a pitch perturbation response. We will cover the dynamic analysis of a full 3 degree of freedom longitudinal motion in the next part of the video.